So thank you very much, Benoit. Thanks to all the organizer for the kind invitation. Before switching to the dinner here, let me try to give you some flavor of what I'm going to talk about. Okay, yesterday we saw a few talks about extreme value theory and Poisson statistics, Poisson distribution in the deterministic setting. Now I would like to switch to the non-stationary setting because I'm working on it since a few years, and just to situate the problem, a brief account of what I mean by non-stationary setting, just in the domain of extreme value theory and of Poisson distribution for rare events. Okay, so for me, this non-stationary setting contains the system of this type that are sequential systems, and then there are random systems. And in the random system, there are the annealed system and the quenched system. And the annealed also, you can find different kind of system to study. In particular today, I will speak about one of them, which fits with the annealed one. Just to give an hint, we can put here some Markov process, and what I'm going to talk about later, the stochastic differential equations. Okay, just a few words about the generation of these systems. I will not talk about sequential because it's not just the goal of my talk, but briefly, sequential systems are nowadays a lot of investigation about them. They are constructed just taking a set of maps. So you have some sets. Suppose each point of this set is a map T1, T2, and so forth, Tn. And then you take a composition of this map, taken just in this set. There is no randomness here, so you don't choose the map according to some probability. And so then you can, I don't know, take T1, compose it with T2, and so on and so forth. You put some measure on this set, usually some ambient measure, and then you try to study the statistical properties of this system. In the framework of sequential system and sequential annealed quenched, I already did some work with George and Anna Cristina Freitas and Magalhães using the probabilistic tool George presented and others and Mike presented yesterday. But we now use different kind of tools. Okay. Now, what is the problem, more or less? The problem is the following. Suppose you have a probabilistic space of this type, for instance, and take an element of this space, let's call it omega, and then you suppose for each omega, you can associate a map, T omega, acting on some space M into itself, right? And now the question is, okay, with this structure, we can construct a skew system of this type, F omega X, which is given simply. Okay, I'm sorry. We have some map here, sigma, the omega into omega. For the moment, it's a measurable map. I am not telling you anything about the regularity or the invertibility of the sigma. Then you can define this skew system in this way. Right? And then if all these objects are good objects, right? There is an invariant, several invariant measures. So there are several invariant measures for F. Okay. And the question you can ask the question if there is some measure, invariant. So you measure invariant for F related to P, related to the marginal P. Okay, the answer is yes. There is necessary sufficient condition. It's more or less, there are co-random measures. So basically, under a very general condition, if I call mu f one of this invariant measure, which, by the way, there is only one, which answers this question, we know that mu f can be written in this way, mu omega dp, so it's this integration, where this mu omega lives on M and are called the conditional or sample measures. Okay, the proof, for instance, of this stuff can be found in the Cruel book about random measures. Now the question is, when is possible that this becomes a product measure? So for instance, is it possible that mu f can be written as rho times p, where rho, of course, lives on M? And the point is, this is possible. If this is possible, rho is called the stationary measure. I'm telling you that because I will use it now in my talk in this condition. Okay, and this scenario here is called the annealed scenario. So basically, the annealed scenario, when you can disintegrate this invariant measure for the skew in this way, this is a product measure between the marginal and the measure which lives on the fiber, which is the same for all the fibers. Otherwise, if you have this scenario here, this is called the quenched one. Now, it's not difficult, starting from this system, to construct annealed systems. For instance, one way, just with this framework here, is to take this space here S, which is omega to the power n, beta to the power n, and p to the power n. And the skew system now will begin here, which is this in this way. Okay, so now I take this omega will be a vector in this space, countably many components, and this will be the shift now. And here you have t. We take the first letters in omega applied to x. And in this way, this is an IID system, annealed ID system, which fits with this property here. And in particular, this rho has a very nice property in this framework here. Rho verifies this integral representation. If you integrate a function which is bounded, this is given by f p omega x in dp omega double integral. Okay. So this is exactly the framework I put myself in this talk, which is the annealed situation. Okay, so this is the ID. So basically, you compose IID map in exactly independent way. All the maps are distributed in the same way. And what is interesting, you get this measure here, which is called the sensory measure, which verifies this property. And we can take this as the underlying probability to do our statistical investigation. Because we are doing some probability, we need some probability somewhere. In the annealed situation will be this one. But if you want stationarity, you have to multiply this one by p to the power n. And what is interesting is we have this representation if sigma here, here is non-invertible. Okay, because if sigma is invertible, okay, instead in the quenched situation we need sigma invertible. Otherwise, everything trivializes and all the mu omega will be exactly equal to the invariant measure for all the t. All the t omega will have the same measures. This is a comment which is in the Arnold book. He stressed this point. For this reason, when we worked on the quenched situation, we were obliged to take sigma invertible, otherwise everything became trivial. Okay, I will not going to speak, of course, about the quenched, but I did some work with an Australian team, in particular, Cecilia Gonzalez-Stockman, Gary Froilan, and Jason Etnick. We developed this investigation of extreme value theory and Poisson statistics for the quenched dynamical system for very general potentials. and using a spectral technique, which I'm going to present now. Instead, I did the same in a different context with, as I said before, with George, Anna Cristina, and Magalish, but using different approach. Okay, after this brief introduction on the kind of random system which I'm going, which I looked in the past, let me go to this new work, and where we study a random system in the annealed situation for SDE. And this is a work we have just put recently on archive with F Flandoli, who is a probabilist in Pisa, Scuola Normale, Stefano Galatolo and P Giulietti, who are at the University of Pisa. And so the idea is the following. Yesterday, we saw a talk about this differential equation, which can be written in this way. So we have a Brownian motion plus the WT with a deterministic part, which is B. And we have an initial condition, which we call small x. Okay, these are the usual framework. The point is we need some assumption on B and on on B, which are written there. Okay, don't ask me what is the real realm of generality of this, because if you want this assumption were chosen to get some results, you will, in particular, we need a theorem, not by us, by someone else, according to which, if we have this condition, we can say something about the probability distribution of the solution of this SDE. You will see in a moment. But it turns out that these conditions are verified in some interesting setting. Okay, now the problem is, since you already see a few talks about extreme value theory, the idea is to create a rare set and to look at a distribution of the first bit in time on this set, which is equivalent to look at the distribution of the maximum of certain observable. And in particular, since we are here in the continuous setting, because the solution of an SDE, given omega, the solution will just occur, right? The time flows in a continuous way. The idea is we have to take some discretized time. I will come back at the end about the relationship between continuous and discretized time. But for the moment, we discretize the time in this way. We take a temporal step, which is called h, and n, and this gives a certain number, a sequence of discrete time, which we called Tn. And so what we did is we take this observable, which has been introduced yesterday, we fix a point x0. Another important, not important, but important for us, assumption is we now work in a non-compact set. Okay? Yesterday, all the talk were about dynamical system defined on a compact set, interval or some region. Here we are working on a non-compact set. Yes, because we take the initial condition in Rn. Here is here it is called Rd. Sorry, Dn is the same. Okay. Okay, so the idea is what? We fix x0. X0 is a point in Rd, a small region around this point, right? And then I will tell you how we choose this radius, because it's just the scaling which is necessary in order to get something interesting and not degenerate. And then we take this observable here, and now we can state our first result, which is this one. If I called Bn a ball around this point, Bn is a ball centered in this point with a radius E minus UN, where UN will be a sequence which will be chosen later on, is written there, what is Bn. Taking this sequence of discrete time, we have this, the existence of this limit distribution, where P is the probability on the yes, let me turn back here. Yes, where the Brownian motion is defined, And mu is the stationary measure of the process, which I'm going to introduce later on, which basically plays the role of this guy here. Okay? So this is just an annealed situation. So we were able to prove this result. And this result is completely independent of the choice of h, which is the temporal step. I will comment about it later on. Okay, then there is another result, which we proved recently. As you saw yesterday, after we have the extreme value distribution, which more or less is the distribution of the first entrance of the orbit, discretized orbit here in the set, which is, my assertion is true because we have stationarity, because this measure makes the process stationary, right? We can ask if the distribution of the number of occurrences in this rare set. So basically, we are bringing to study this sum here. You yesterday saw this, even in my talk, I spoke about it as well. Of course, if we want to have some meaningful results, we have to normalize this sum by what we can call the cut scaling. And if we do this, we get, this is what we want to prove. I mean, we want to prove that there is some random variable in some probability space for which the distribution, the mass distribution, is the result of this guy here. And what we prove is this mass distribution is just given by a Poisson law, standard Poisson law, not a compound one. And I will show you why it is standard and not compound later on. So this is the second results. Okay, now, how can we get this result? Okay, as I told you, this is based on a probability theorem, which gives us the distribution, the probability distribution, no, the density of the probability distribution of the solution of the FDE. This result is due to, yes. So in the paper by Benozzi, Pesce, and Zhang, the question mark is because there was some reference. They gave a result about the density of the distribution of the solution, right, for some SDE with some assumption on the coefficient beta, which I introduced before. So basically, what is important just is the flavor of the result. Here there are some technical assumption on the quantities which will enter the result. But basically, what is important is to have this kind of Gaussian, where which is associated to the following results, which is this one. Okay, so basically, what is STXY? STXY is the density of the distribution on the random variable given by x, big X, t, small x, where small x is the initial condition. So basically, you have to think to this as a random variable, of course. We should write it in this way to be more precise. Yeah, but as probabilities do, I'm not a probability, but the probability, what they do is they forgot always to put this guy. This lives on the probability space. And so this is a random variable with two index, x, small x and t, and you could ask yourself, as this random variable, some densities, or is discrete or continuous? If it is continuous, does it have some densities? The answer is yes. And this density is given by this object here. This is the kernel of the density of this variable, where, of course, y indicates the value on R of the on Rn of the variable, and x give you the, sorry? No, density is this object here. No, we just state, of course, yes, of course, no, just. This is just the one quantity which entered the density distribution. And it's a very nice theorem because not only gives you how the density behaves, upper and lower bound, but also some bounds, which we use, by the way, on the partial derivatives of this density. Okay, so now let's go to our stuff. As I told you, I want to use a spectral technique. Okay, this spectral technique is very powerful, very useful, right? I presented it several times. is an alternative technique to the probabilistic technique which Mike, George used. It is in particular useful when we have system with a spectral gap. I will tell you what it means later on. And in these cases, if not, okay, we must be careful, but I think if the system is not uniformly expanding, we can transpose this theory by induction. At the end of his talk yesterday, Mike said, in order to verify his condition A1 and A3, one could go to induction. So namely, you prove what you want on induction scheme and you bring back to the original system. I think this is also possible here, pretty sure. So it's not so narrow, this technique can be generalized. By the way, the first problem was to define this operator. This operator will play the role of the Koopman operator in the framework, in the anneal framework. So basically what you do is, you take the expectation with respect to P of any function, bounded function, composed with the solution of the SDE with initial condition, with initial condition X. Where is here? Initial condition X. And then, since you have this solution as a smooth density, you can write this operator in an integral way, as we do usually in probability. We know this, but we aren't in this way. Okay, now if we have this integral representation for this operator, which is called the Kolmogorov operator or Koopman operator in the deterministic setting, okay, now we can introduce our favorite operator, which is the transfer operator, which is named the dual of that one. So basically, if we have some measure which we can write in this way, absolutely continuous, which is back to Lebesgue, right? We can write this in this way, just using the integral representation of the Kolmogorov operator, and it turns out that this allows us to define this operator here, right? Which is the dual of this one. Just look at this equality, and this operator here is called the Perron-Frobenius operator or transfer operator. And in the framework of a anneal system, it's just a sort of average of, we don't have maps here. But in this framework here, the anneal transfer operator is just the average of the operator associated to each map. Here we don't have maps, but more or less the meaning is the same. And this is a very useful duality, which allows us to link the Kolmogorov operator with this with the transfer operator. Okay, now we have to introduce the noise, because the noise for us is, sorry, not the noise, we have to, yes, the noise, because now we have to perturb this operator, and the perturbation is just given by the fact that we have to modulate this operator with the presence of the rare set, which is this ball here. So the way we do it is just to introduce this perturbed operator here, which is the unperturbed operator. T is the temporal step. Since all these results are independent of the temporal step, we put T. In some cases, I put H just because it's important to look at the temporal step. This perturbed operator is written in this way, right? So in all the work I did before, this characteristic function was inside the operator. Here, for some reason, no, because it must be in this way, by the way, it's outside. It doesn't change too much, but it's not what one would expect if instead of having solution of SD, we have composition of maps. By the way, this is outside. Now, why is a perturbation? Because when n goes to infinity, the radius go to 0, and the perturbed operator became the same. So the idea is, since we want to have information on the spectra of this operator, this can be recovered if we know the spectrum of the unperturbed operator, just with a small perturbation. By the way, this operator, two operators verify again the duality condition. And then we have this first lemma, which is proved with probabilistic issues, which allow us to relate the Kolmogorov operator to the average with P of the characteristic function of the solution of the SD in the complement of this ball. You will see that this equality is important for what we want to do, because the object is to prove statistic of, is the value distribution and Poisson, and you will see at the end in the proof that this is the quantity which we need, and this quantity can be expressed in terms of the Kolmogorov operator and then in terms of the Perron-Frobenius operator associated to it. Okay. Now, the functional space. Since we work on Rn, we need some appropriate spaces, and these spaces must, since we want to use spectral technique, they must be related one to each other in some way. So first of all, in order to have something go summable, we have to take, and since we work with Lebesgue, we have to take, we have to define L1 with this weight here. So basically, we need functions in our space which decay at infinity once we multiply by this function, which instead grows to infinity. And then we are using this oscillation space, which has been used with success by Benoit, but we have to modify it a bit, since the original space was studied on compact domain. Here we are on RD. We have to integrate here not with respect to Lebesgue, but with respect to a measure, which is absolutely continuous, with some density. And the density is basically has the property to have the Radon-Nikodym derivative, which is bounded. And with this space, with our functional space is defined in this way. So we take the oscillations, which is a sort of semi-norm, modified as we did with this measure here, which is absolutely continuous, and we put the L1 with this norm here. And now we have to prove that this is a good space adapted to what we want to do. Actually, it is not difficult to prove that this is a Banach space. And also, this space here is compactly embedding in L1, not L1 of alpha, but the real L1. Because at the end, what we need is to choose, we have to choose two spaces in this deal, you know, a strong and a weak space, right? And the weak space will be this one, not with an alpha. And we take alpha equal to 2, but it must be the real one. And the weak space, the strong space will be instead the BV, and BV alpha is constructed with L1, which expect alpha equal to something. In our case, alpha will be 2. So there are basically three spaces involved here. This one, L1 normalized in this way, and the real one. Okay. Now we have some regularizing property, and it is here where the stochastic calculus enters, because up to now everything was more or less classical, but now we need to use the stochastic part of our work, and in particular for the perturbed operator, which I indexed with H. We were able to prove some regularizing property. The most important lemma in the paper is this one, because here probably stochastic calculus enter using of Ito formulas several times, plus all the conditions given by the theorem which I stated before, by Mengozzi, Zhang, etc., where they really use properties of the SD. Okay, this is the basic lemma, where the probability of stochastic calculus enters in a heavy way. And we don't have this kind of result for maps. You will see this will allow us to simplify a lot. And for instance, due to the smoothness of the densities of the solution, for instance, we can prove this condition here. Namely, if we take a function which is in L1, it will be regularized that we can see one function on RD. And all this follows by this previous lemma. Okay, so these are useful properties if you want to do something concrete. And then we have finally the Lazotov inequality, which is proved for the perturbed map on the space BV2. 2 means we choose alpha, which gives the growth of the function of the test function at infinity equal to 2, and the weak space will be L1, real one. And we have the same, which is for the perturbed operator, or with different constant. Okay, lambda is less than 1, so it is the usual Lazotov inequality. This one. Okay, then we have to use this perturbation result. I already presented it several times, so I will go fast unless you ask me. The issue is we have unperturbed operator which verify this condition here, right? We have to suppose that the top eigenvalue of this operator is simple, and there are no other eigenvalue on the peripheral spectrum. So basically, you have one, which is not only ergodic, but mixing. And we can prove in our system this is true. This needs to be proved. But so let's suppose one is the only eigenvalue, simple eigenvalue, no other eigenvalue on the peripheral spectrum. So the question is, what can we say on the top perturbed eigenvalue of the perturbed operator? And this is done by using a perturbation theory developed by Keller and Liverani, and which basically tell you the following. If the suppose the perturbed and unperturbed operator, both of them verify this quasi-compact condition, right? And epsilon here means a perturbation, which cannot be zero. When it is zero, it is the unperturbed operator, right? And then we need some decay of this operator here, Q. So basically, you can forget Q from the very beginning, and you see here how the perturbed and operator should verify. And phi epsilon will be the fixed point of this operator, and nu epsilon of this dual with the same multiplier here. Then what we need, I go fast, but you can read. What we need basically is a distance between these two operators, and this distance is given in terms of the unperturbed conformal measure, mu zero. Mu zero will be the fixed point of the unperturbed operator, which is not the invariant measure, but is the conformal measure. Think to Lebesgue in our case. And then we need also this condition here. So basically, okay, this condition here is called the triple norm. We have to look at the distance of these two objects with respect to the norm of the Banach space. And then we have to verify technical condition, which is R3. If we have all this, and in our case, we have to prove all this, but let me tell you something. If we have everything for L0, so if we have everything for L0, so if we have quasi-compactness for L0, plus this distance, which can be managed in some way, this holds, right? More or less. But then there is a final condition, which is important in our setting. The lambda epsilon is the eigenvalue of the unperturbed, of the perturbed operator. This is related to the eigenvalue, which is 1 in our case, of the unperturbed operator by this sort of linear response condition. And what is important is what is this theta. That epsilon is the distance between the two, and theta is given in terms of this object here. This object here, one should prove they exist, in particular this limit exists, and if the limit exists, this theta constructed in this way is what yesterday was called the extremal index. Here, this extremal index came from this theory, and this object here are computable. In our case, I will show you in a moment, very easily computable. Otherwise, if not, this is the basic ingredient of all the tools in order to do extreme value theory or statistic of Poisson, is to compute these guys here, written in this way or in another way, but this is unavoidable. At a certain point, you have to put the main really and compute these guys. Okay, but if you can compute it, and okay, it's very not difficult to prove that this theta is, this sum is always less or equal to 1, so this guy here is not negative. Then we have the expansion of the perturbed eigenvalue in this way. And okay, now let me show how we can compute it, that all these guys are 0. So the extremal index is 1. So we have really what Gamble law, pure Gamble law. And the reason, if the proof is there, is 2 lines. The reason is here, you see, this is defined in this way. If you define this function here, f kn, which is the first part of this strange expression for the Q, look, the Q is given in this way, I took a part of it and I've written this way. So this Qn is given by this limit here. Okay? Now, the difference of the two operators is given by the characteristic function of the ball times the unperturbed one applied to this function here. But then I use order. Because, okay, I take L1 for the measure of the characteristic function, so it's the measure of Bn times this guy here, we know it is in an infinity because this function is in the good space. But now by the regularity property, which of course do not work for usual dynamical system, here we have a very nice property that this guy here is bounded in L1. If it is bounded in L1 here, we see another Lebesgue measure of this small set coming. So basically we have the Lebesgue measure of this set, time M is Lebesgue, sorry, time another Lebesgue measure coming from this bound here, divided the invariant measure, the stationary measure, Bn. But this stationary measure is absolutely continuous because the density was absolutely continuous, Stx. And if we take Bn, okay, we can prove by the Minkowski-Zhang condition that we have surely in a lot of points the density which is bounded from below by the condition on partial derivatives. So mu Bn and lead Bn differ by a constant. And so this goes to 0. And all these are go to 0. This is pretty nice, but it comes from this property here, which of course we don't have with a dynamical system. We cannot do the same trick. Okay, and then here is the proof. The proof is very simple because what we want to prove is this annealed measure, right? We have to take, we have to express this annealed measure, this one, and we've written in this way. You can check, it's very easy, very standard result. Yes, using two measures here, the measure on the probability space and the stationary measure, which is unique. And thus we can prove uniqueness by our term. Can be written in this way. But then this can be written in this way because I told you this expectation can be written in terms of the Kolmogorov operators, and this composition here is exactly equal to the n power of the perturbed operator applied to the density of the stationary measure. Okay, but now it's done. Because if we have this, now we can, since we have quasi-compactness, supposing we can prove it for the unperturbed operator, we can decompose it in this way, where this will be the perturbed eigenvalue. We don't know if the eigenfunction, which is called here mu hn, is a measure here, but it's a functional. So it is a function, not necessarily a measure. We don't know. We were not able to prove this a measure. But anyway, it's well defined as an element of the dual of the Banach space. And so, in particular, from the theory of Keller-Liverani, it follows that this guy is equal to 1. It's not difficult to prove it. So basically, using all this nice information, right, we can insert it, plug it into this one, right? And then this is the proof. We write lambda. Okay, this is what we have. Then, since the Sternberg index was 1, lambda can be written in this way. So you take it to the power n and you plug into here. And this is the some nice surprise games, because forgot all this piece here, we came to this one. And now if you want that this sum is non-degenerate, we have to put some condition on the choice of un, right? And this condition is exactly this one. Let me stress that this condition for us came here. We don't have to put it at the beginning. This is, I think, a small advantages of the spectral technique. We don't need to put this boundary condition at the beginning. They came for free, but they came at the end as necessary sufficient condition in order to get non-degenerate limit. We are not to put at the beginning. And so if we put this, which is, by the way, exactly what we need, we have convergence to the Gamble law. And this is the first result. Now, let me go briefly, unless you have questions, to the second result, which is really related to it. We want to prove the same for the Poisson statistics. Okay, and we discovered 1 year ago, more or less, that we can do the spectral technique as well, because what we actually do is not to compute the distribution of the number of visits, but the characteristic function. But there is a one-to-one correspondence between the characteristic function and the mass distribution, and we can go from one to the other by the Levy inversion formula, because what we do, we compute the characteristic function of this observable here. Okay, this is the characteristic function, right? And again, weighted with this annealed measure, and it turns out that this is immediately equal to the expectation of this variable here. Then we introduce the operator, the perturbed operator, which is now again a singular perturbation, but is given by the exponential is times the characteristic function of the small set. And again, we have the correspondence between the Kolmogorov operator and the transfer operator. So basically, this characteristic function can be written in this way. Where now this is a new unperturbed operator which has this form here. We perturb this is characteristic function. So again, we put the machinery on and see what's going on. And it works because we can do the same as before. Yes, and in particular, we can prove again the distance of the two operators now is given by this term here. Again, all the QK have the same form, of course, with different operators here, because this is written in a different way. But still, we can prove this QK are all equal to 0, again, by the regularizing property we have. And at the end, we get that this guy goes to the pure Poisson. They are not compound or whatever. They really go to pure Poisson. So basically, what we prove is not exactly this. We prove that the characteristic function is this one, which is continuous. This characteristic function is continuous in 0. The limit is continuous in 0, so it's the characteristic function of some variable. Then this variable is discrete because it's the limit of discrete random variables in distribution, and moreover, it is infinitely divisible. Because if you divide S by n and you multiply by n, you get the same. So it's an infinitely divisible. And if you take Feller book, a characteristic function which is infinitely divisible and discrete is compound Poisson. And in particular, here is really standard Poisson because we know by the textbook that this is the characteristic function of a Poisson random variable. Okay, let me tell you something. If it is not like that, we have example for maps where we don't get this, but we have some more complicated, but still we know it's a compound Poisson, and we can invert it sometimes and get the mass distribution. In this case, the mass distribution is like this. Do we have sometimes more? Because I want to present you the final part, because the question which could be addressed, natural question, is how all this result depends on the choice of the temporal step. Okay, so let me tell you, first of all, that it's not easy for us to compare what we did with what is known in literature. We asked also experts in this field. We counted at least 3 papers where people really try to do the statistics of this type for stochastic flows. And it's not easy for us to compare what we did with what the other did. Okay, I'm not really a probabilist, I'm going to probability more and more, but there are one very strong probabilist, which is Sandro Vaienti, and we were unable really to understand the real connection of what we did with what the other did. The 3-4 papers, not more than that. We are trying to do it because the idea now is to go to, we say, to 0. But we think a lot about why our model is independent of age. I mean, provided this is right, it could be a mistake somewhere. We didn't find it. If there is a mistake, everything collapses. And so, sorry, but for the moment it seems correct. So why it doesn't depend on age? Okay, first of all, let's give a case where it depends on age. Okay? So the example is this one, but you will recognize it immediately, something related to clusters. So basically, we define variables, we define groups of variables from 1 to n, which are all equal to some given random variable. So you know we have blocks, or n blocks of variables, which are all equal, each block to some variable, x1 to xn, and all these variables have the same distribution and are IID. But you see, you have a lot of variables which are equal to, in terms of what George and Mike told yesterday. This gives you clusters if we think in terms of maps. Here there are no maps, there are random variables here. Probably this example I don't read in the literature of really small example in extreme value theory because they're very easy. But just to give you a flavor. And if you do the computation, exactly the computation, as we did in the textbook, when you ask a student to prove that the extreme value theory, you take IID random variable, right? And then you say, okay, compute the distribution of the sum, and at a certain moment all the variables the same distribution, and then the student will discover that if we don't choose UN in a given way, you go to 0 to infinity. So we have to choose un in the good way. Okay, if you do exactly the same, you discover that we came to this limit here. So we have the extremal index here, which is 1 over n. Of course we have, because we have maps which are grouped, and so these are clusters in the language of what we saw yesterday. So it's not surprising, it's very... Now the question is, can we have something a little bit different, but not too much, if we modify a bit what we did here? And here we give this example Franco found because he was so worried about what we did. So the idea now is to modify a bit this example, nothing to do with SD, nothing. It's just a toy model, just to try, heuristic model to try to understand what's going on. So we take the same, exactly the same, but now we modify the y adding other variables, W1, Wm, with some distribution, which I'll give you in a moment. So basically, this variable moves the x1, xn, which contributed to create the clusters a bit. And again, these W have the same distribution, but are not anymore discrete. They have some continuous distributions. So now you create this new process, because now we want to compute the distribution of this process constructed in this way, exactly as before, but now we add the W. And now the law of this new variable is the convolution between the law of the x, which is the same as before, times the law of this new variable which we add at each step. And in particular, we asked for this law of this small perturbation of the previous one. They should verify this condition here. Basically, they diffuse a bit, are not just delta functions, as in the previous example. And with this assumption here, we are, again, with this, of course, normalizing condition, which is more or less always the same, right? In this, we get, again, the pure Gamble law. So what is the heuristic, I repeat, conclusion is the following one. If h is small, the Brownian motion, right? The pressure of the Brownian motion makes the system lose memory. So when h is small, the temporal step is small, we expect basic independence, so we expect E minus t. But when h is small, the small fluctuation of the Brownian motion restore again the independence, what we wrote here. To summarize, it's just the end of my talk, but I want to repeat exactly what we wrote because it was what in the paper. The two ingredients who seem to have fundamental importance are the loss of memory plus this local fluctuation which is given by this measure here. So in some sense, this example comforts us that even if h is small, the local fluctuation given by the Brownian motion makes the process independent, and it's for this reason at the end we get E minus tau. The next step would be really to see what happens when h is equal to 0, basically to do the continuous case. As I told you, there are a few results in this setting. We are not able for the moment really to match what we did with this result, but this is something which is in progress. The novelty of if our work is we try to put together two different approach, the probabilistic one and the dynamical system approach through this perturbation theorem, and we get what we got. Okay, I stop here. Thank you very much.